Hello, today I'm going to be speaking about some of the work that I've been doing in the last year or so about the validation of indoor GML files. My name is Hugo Ledoux, I work at the TU Delft, and my work was part of a bigger project that is called INOS, and the aim of that project is to create an ecosystem for indoor GML files. But first, let's start about defining what indoor GML files are. Indoor GML is both a data model and an XML-based exchange data format for modeling indoor spaces. And what's special about it is that it has an emphasis on navigation application. It's a standard of the OGC. It was first standardized in 2015, and the current version is version 1.0. The main idea behind Indoor GML is to semantically decompose the indoor space of a building into cells, which are deemed as the simplest unit useful for navigation. Example of cells are rooms, corridor, or staircases. In Indoor GML, we would typically not model architectural components such as windows or furnitures because they are not deemed important for navigation. What's special about Indoor GML is that we don't only store what we call the primal subdivision into cells, but also the dual subdivision. The dual subdivision is the navigation graph. So basically you can look at the details in the paper, but we would typically take every cell that we have in the primal, find the dual, which is a vertex, and then we build a navigation graph that basically tells us that we can walk from one place to the other inside that building. So let's go back to our goal, which is to validate an indoor GML file. In other words, if I have an indoor GML file, I would like to know if it respects the rules in the OGC specification, which is this document here, a 100-page Word document that gives me all the definitions for the different XML elements and gives me which XML elements are allowed to be parent and children of each other. The OGC document also comes with a set of XSD files, so XML schemas that help me validate a few very simple things in an indoor GML file. So for example, you can use your favorite XML editor, for example here, and then if you click validate, it will help you to make sure that all the XML tags are good and that the value that you fill are okay, but it will not help you to validate more. The XSD validation is not enough to ensure that the file can be used by other people. So for example, if I would like to take my indoor GML file and give it to someone else so that this person performs indoor navigation with another software, simply using the XSD validation is not enough. It's possible that there's a lot of errors in my file. Errors that have to do with geometry, but also how the primal and the dual subdivision are connected to each other, or they're really synchronized. So what I did is I took the OGC specification and I read the whole document, and then I tried to find sentences that could be translated into axioms, into things that can be objectively validated, and later on that can be translated into code so that I have a software to perform the validation. I developed a methodology that contains 6 steps. The first step of the methodology is the schema validation, as we've just discussed. So nothing special there, we just use normal software, can also be done with code. The second step in the methodology is verifying that the geometry of every cell in the primal, which is a GML solid, is valid according to the ISO 19107 rules. For this step, I didn't invent anything. I didn't need to develop anything. Basically, I reuse part of the work that I've done in the last few years for the validation of 3D city model, and I reuse code that I had developed for the software Val3D, which, for example, takes all the geometries in a city JSON file and validates them one by one. The third part of the methodology checks the X-links in the indoor GML file. Indoor GML heavily relies on X-links, which is one mechanism to link between different objects in an XML file. For example, if you see here, we have a primal cell, and you can see here that the duality is using an X-link, and it links to an object that has the ID R1 in that case. So it means that somewhere in our file we have an object that has the GML ID R1. So then if we just search it, yeah, so now we found it. So you see we have somewhere a state. So a state is a node that has the GML ID R1. And if you see, this GML ID also links back with the X-link to the cell C1, that was the GML ID of our original cell, and also links to different edges. And as you can see, another vertex somewhere in the file has many edges that are incident to it, and all of them are using X-links. So basically this steps only checks if these X-links are coherent, which is something that cannot be done only with the XSD schema validation. Okay, so now step number 4, which is checking the overlap between all the three-dimensional cells in the primal subdivision. So if we look at the building that we had, so one simple building which has 3 stories, basically what we need to do is we need to take one room, which is a three-dimensional solid or volume, and we need to ensure that it does not intersect, or its interior does not intersect with the interior of any other rooms. This is a pretty standard test in three-dimensional GIS, but here we have to be careful because the number of intersection tests that we need to perform will grow exponentially. So for example, you will see later that we have a shopping mall in Korea that has about 3,500 rooms. So if we test them all, then it means that we need to do more than 12 million intersection tests in 3D, which are pretty costly. So it means that we need to be careful for the implementation if we want to obtain software that is usable in practice. The step number 5 verifies that the adjacency in the primal subdivision is the same as the adjacency in the dual subdivision. So if we take, for example, this very simple Indoor GML dataset where we have 3 rooms, C1, C2, and C3. So what we do is that we take one cell, let's say we take C1, we take the dual of that cell, the vertex, and then we check all the other vertices that are incident to that one. In that case, we have only one, and that's the vertex that is dual to the cell C3. So in that case, because the dual of C1 and C3 are adjacent, we also need to verify that C1 and C3 in the primal space are adjacent. So we take the 2 three-dimensional cells, C1 and C3, and then we ensure that they are adjacent by checking that they are really touching on their boundaries. And obviously we do that for all the cells in the primal. And the final step, step number 6, is pretty simple. Basically what it does is that for every three-dimensional cell or room in the primal subdivision, we get the dual vertex, and then we make sure that this vertex is geometrically located inside the room or the cell. So if we look at the same data set here, we have several rooms that are located over 3 stories. So if we look at the dual graph, it looks like that. But basically what we do is that for every room, we take the sole vertex, so there's only one that should be dual, and then we basically perform a standard 3D test point inside polyhedron. The 6 steps of the methodology I just presented were implemented into the open source software Val3D. Val3D is a software for the validation of 3D primitives according to the international standard ISO 19107. It started around 10 years ago. I'm the main coder. And it used to validate only solids according to ISO 19107, but it has since evolved to be able to validate any of the ISO primitives, these ones, and also special support for specific formats is available, for example, for CityJSON, if you want to validate 3D city models. It's a command line interface software that you can just simply download. So if you're using Windows, you can download the binaries directly. And if you're using Mac or Linux, it's very easy to compile. If you use Mac, actually, you can just use Homebrew, and then you can just type the commands there, and then you have Val3D in your computer. Valtridity can or could, before I started this project, read natively CTJSON, OBJ, and a few other formats. For example, that's how you use it. So it's only from the command line. So you type Valtridity, the name of your file, and directly you get an overview of what's in the file, what is valid, what is invalid, and also you get, if it's invalid, then you get a error code that tells you what is invalid. So for this project, what I did is I added a parser for IndoorGML files. So now Valtridity can read directly IndoorGML files. And also I added new error codes that are related to the 6 methodology step that I just presented. So now if you want to validate your file, you can simply get Valtridity, the latest version 2.2, and then you can simply do Valtridity, the name of your IndoorGML file, and then you get, as is the case for other format, a summary of what's happening. If you're interested in more details, you can simply generate a report. That's a JSON report. So if you generate that report, that's a file in your hard drive. So here I'm generating a report that I called r.json. And if I want to understand that file, I can simply go to the URL there, geovalidation.bk.tldel.nl/valtridity. And if you drag your file there, then we have a browser for the report. So there you can understand the errors. You can click to know more about certain errors. You can also explore where are the errors. So basically we tell you that there's a specific error. If there's a hole in your shell or somewhere, you get the location of that shell, but you also get the ID. So it's possible to understand where the errors are, and then potentially you can go fix them yourself after that. For the experiment, I collected all the publicly available IndoorGML files. After browsing the web, checking on the official website, emailing a few members of the OGC IndoorGML SWIG, I managed to get these 8 files. Only 8, you might say? Yeah, for a standard that's been around for 5 years, I think it's very disappointing that this number is so low. If you look at the 8 files, you might recognize some of them. For example, the FJK and the FZK are 2 files that have been around as IFC files for a few years, so they were simply converted to IndoorGML. Then we have a few other files. Most notably, we have 2 buildings in Korea, LWM and the Dome. These are real buildings that contain several thousand rooms. I ran all the 8 files through Valtridity, and here's an overview of the validation report. First thing to notice is that one file, KUang, had an invalid schema, which meant that at the end the software basically crashed. Another thing to notice is that none of the 7 other files are 100% valid. So if you look only at the primal cells, only at the geometry, then basically only one file, the DOM, has all its nearly 2,000 rooms that are valid GML solids. But some of the files have only 14% and one file has 0%. The good news is that many of the errors are very simple errors, for example, duplicated points. Then if we look at the IndoorGML errors, we can see that again, all the files contain errors. Only one file has one error, but a lot of them have several errors. Some of them, for example, the DOM, while it has 100% of valid primal cells, it has about 1,200 overlap between these primal cells. A concrete example of the error 701 cell overlap is with the nav demo 201 dataset. This dataset has 6 such errors. And if we zoom in on one that we obtained from the report, then if we take one floor, for example, in 2D, and we zoom in on 2 of the IDs of the cells that overlap, we can see that this overlap is of the magnitude of a few centimeters, so maybe 20 or 25 centimeters. But then if we look at another file, LWM, where we have several hundred such overlaps, then we really have gross errors there. For example, if we take the data set, one floor, and then we just look at cells that overlap, then we can see that these cells are completely overlapping. That is, one cell is completely located inside another one. Now I know what you're thinking. Does it really matter if my IndoorGML files are not valid? To that I would answer, well, it does, unless the only thing you want to do is look at your IndoorGML files. But then if visualization was your sole purpose, then I don't think you should be using IndoorGML in the first place. OBJ or Collada are much better visualization format. They're much simpler, much faster, and way more software will support them. IndoorGML was developed in the first place to allow for complex operations like indoor navigation. So most of the errors that Validity highlights are actually a problem. So if you took any of the 8 files that I tested in the experiment and ran complex operations on them, then most likely the process would either crash or give the wrong result. So I advise you, if you're using IndoorGML, to download and run your file through Validity. And if you produce new files, if you could please share them with me or with the community, that would be nice, because only having 8 files is a bit of a problem in practice. It would be nice if at least we went up to 10 files. Bye.